Hi, so I'm Shramali Chatterjee, an assistant professor in ag and biological engineering, housed in both the colleges of engineering and agriculture at Purdue University. And I will be talking today with my awesome student, Karthick Shankar. He did his undergrad in electrical and computer engineering at Purdue, and he was part of my lab. And unlike, many undergrads, who tend to write second author and third author papers, it's not a bad thing, but just given the fact that Karthik was enterprising enough, he led this paper called Janus, which is a benchmarking effort of sorts for cloud analytics, edge analytics, and computer vision analytics. So with that, I will get the conversation started. So conversation with my undergraduate student, Karthik Shankar, who is now a graduate student at Karthik will tell you where.
Yeah, thanks for the introduction. I'm Karthick Shankar. I am currently a master's student at Carnegie Mellon University. And like Professor mentioned, I was working with the ICAN lab for about a year and a half when I was at Purdue over a bunch of different topics ranging from IoT, distributed databases, database tuning, and even cloud computing with serverless.
So can you give us a little bit of vision for this paper and maybe segue into some of the projects that you have done in serverless at a high level that are in various stages of publication?
Yeah, so the main motivation for Janus is the increasing amount of IoT workloads. And there's this pretty interesting fact that IoT devices that are, being used in terms of the amount of total devices that are shared connections between each other. So IoT devices such as smart homes versus devices such as phones and cameras and laptops, for example, that ratio has been increasing in the favor of IoT year over year. And in 2020, actually, it was the first year where IoT devices made up more than 50% of the data connections between different devices. So there's a big interest and there's a big opportunity in that space. So our motivation for this paper essentially was to identify various IoT workloads, which are a data light workload in terms of anomaly detection and data heavy workload in terms of object detection, and use these workloads with different cloud providers these days, the Amazons, Google, and Microsoft, and look at how their services compare against each other in both these workloads and see the trade-offs that we can pick and their pricing models that we can pick in order to optimize for a given application.
Okay, so very nicely put, Karthik. So let me break it down a little bit, and then maybe we'll go a little bit into the specifics of the different kinds of benchmarking we did for this paper. So I think we went a little bit out there and did lots of different technologies in one within the ambit of this paper, and there was a reason for that, right? Because I feel like IoT has under its umbrella a plethora of technologies, and not one size fits all, right?
Yeah.
So not about just cloud computing or edge computing, cloud being the centralized model and edge being the decentralized model. There's all the gray area in between. And I think the more we can make use of this bring your own device model, the different grayishness in between the cloud and the edge, the more we can use compute in a very efficient manner. So Karthik, can you tell us a little bit about how you think some of the kinds of technologies that we have developed, such as Sophia, Optimus Cloud, etc., may actually help with the efficiency of using data centers and efficiency of using compute in general. And that also nicely segues into Janus, where we had this benchmarking effort.
Yeah, so optimizing resources on the cloud has been a very big research topic for many years. And especially in the works that you mentioned, Sophia and Optimus Cloud, what we are essentially trying to do is optimize databases to be able to adapt to dynamic and varying workloads. Because nowadays, people use these distributed, reliable cloud databases for a bunch of different applications for their given organization. And so that introduces a need for this automatic tuning of these databases to be able to optimize on the price per performance ratio. And so what we want is to pay less and still get the most amount of performance out of it. And so that involves some non-trivial effort in order to be able to analyze workloads, analyze the patterns of their read-write characteristics, and finally tune a given database to be able to use those workloads. And so that naturally segues into our work for benchmarking, because again, there are so many different options to pick from, right? Even not looking at just databases, looking at like IoT orchestrators, for example, there's a bunch of different options that we can pick in terms of AWS Greengrass or Google IoT Core or even Azure IoT Hubs. So there are many different options and many different tuning parameters that we can pick in order to run our application.
Yeah, so very nicely put. And I think another important thing that you mentioned is for a lot of our algorithms, such as Sophia and Optimus Cloud, which is, by the way, which involves a whole bunch of people, including a very talented graduate student, Ashraf Magoo. So Ashraf and Karthik have been working together very well, spearheading different parts of the effort. And something that we realized is it's not just about performance, right? So if you throw all the money at things, you can buy the best VMs, right? The most well-resourced VMs. But obviously, not everyone is a Google or Amazon. But even if everyone were a Google or Amazon, I think you have algorithms such as ApproxDet and all these efficiency-centric algorithms these days that you do want to throw all the compute possible at these different workloads, right? So one of the things that our lab has been doing is how can you right-size the compute rather than over-provisioning or obviously under-provisioning these resources, right? So I think in a data center, there is some almost like counterintuitive statistics, something like 10 to 15% of a data center is used at a time, like because
that's very interesting.
I might be exaggerating a little bit here, but I remember when I heard the number, I was like, wow, that doesn't make sense. But one of the reasons they do that is, if you are on the consumer side and you see that, hey, there is downtime, then, well, I cannot deal with downtime. And that is something that happens in some of the smaller organizations. For example, the work that Karthik and Ashraf did, that is funded out of National Institutes of Health grant. It was an R01 grant. This is the final year running. It's with Purdue CS, Purdue EC, and Purdue ABE, and Argonne National Laboratory in Chicago. So Volker Meyer there. And what happened there is, like NGRAST is a metagenomics pipeline, and that was one of the kinds of workloads that we profiled for our Sophia and Optimus Cloud paper. And one of the things that they wanted to make sure is, as you have more and more of these microbiome / metagenomics data sets, you don't have too much downtime for the consumers, right? So you have these microbiome researchers there. It would become a real problem if you would under provision the resources. You might run out of, compute for the clients all across the world, right? So there it could be an under provisioning thing. But in general, if you think of the data centers around the world, typically they over provision by a lot so as to make sure nobody is out of compute, but that can have really untoward effects in terms of the environmental effects of these data centers. So right sizing compute is a very important thing that is featured in our data engineering kind of efforts. So I think here it's a little more data sciencey. I think it's a nice mishmash of data engineering and data science, because it's hard to do one without the other. So sometimes I struggle to say, is Janus a data science effort or is it a data effort, right? What do you say, Karthik, in terms of the data engineering side versus data science?
So as you mentioned, they're definitely very interlinked, right? I feel like Janus in particular is closer to maybe a data engineering kind of work, because what it really induces the developer to think about is, how their data is structured and how they can utilize the different price models. So they have to structure their application in a certain way to be able to take advantage of a given cloud provider and their pricing model. And so more than just the data science analytics that comes out of, like, let's say, collecting farm sensor data, right? More than that, for deploying the entire end-to-end solution, I think there's a lot of data engineering effort required to be able to customize it to the given cloud provider.
Yeah, so I think one nice thing that Karthik did in this paper is he used a Docker emulator to be able to emulate the different kinds of SoC, system on chip specifications that you can get from real SoC devices, right? So Karthik, can you give us a little bit of a flavor on how we had these emulated devices using Docker containers to simulate various specs of SoCs in our experimental testbed?
Yeah, so Docker containers are essentially lightweight, bootstrapped operating systems that run on top of a host operating system and kind of reuses some of the important system calls from the host operating system. So it's a little abstracted away from a virtual machine where it's not a full-blown operating system that to a user looks like it's its own independent unit, except from a Docker container's perspective, it's a little more lightweight, it's fast to deploy, and it has some of the same network characteristics as the host machine. And so there's been a lot of work in this space of trying to use Docker containers and emulate them as more powerful IoT devices, because IoT devices these days are also getting very powerful, especially the fleet of embedded units given by NVIDIA, like the NVIDIA Tegra and things like that. They are very high-powered embedded IoT devices. And so using Docker containers to be able to simulate, let's say, 1 core of a 32-core Xeon machine and 1 gigabyte of RAM, I think closely approximates the performance of a very powerful embedded system.
Yeah, so nicely put. And I think if Karthik had been physically still there at Purdue, he's obviously a graduate student at Carnegie Mellon now, but he's still working with us. And so I think geographical distances don't matter these days. So we actually have a pretty global lab. We have 2 students who are working from IIT Bombay, and then Karthik is working from CMU. For a while, we had a student from Cairo University who was working on an NLP related project. But regardless, one of the things that we have in terms of toys in our lab, right, on Christmas Day, actually right after Christmas, we actually got a whole bunch of NVIDIA devices. So we now have Jetson Nanos, we have Jetson, the Xaviers, and we have 2 different flavors of Xavier to play with various kinds of GPU specs. We also have Jetson TX2s. So one of the things that we're doing is if you have this kind of a heterogeneous test bed, right, you can think of like a fleet of self-driving cars, and every car is going to have a slightly different spec. In fact, Xaviers are there in self-driving cars, right? So now we have various different ways of emulating and simulating test beds. So on the one hand, we have these test beds in the wild, right, where you can't just take your Jetsons and bury them in the soil. You have to ruggedize them and make sure they are ready for an agricultural setting where, it will possibly be cold and raining and, snowy on one day and like turbulent another day. Versus a controlled environment, we have an embedded test bed in our lab where you have, these are connected using Wi-Fi connectivity in the lab, where you have multiple Jetson Nanos, multiple Jetson TX2s, and multiple Xaviers that are connected together. And then you can simulate some of the higher compute environments that could be required in the living lab, right? So for example, if you're doing computer vision workloads, which is a very common workload to perform in the wild, you can basically use some of these expensive backends to try them out in this embedded controlled environment. And then once you've tried them out here, you can ruggedize them and set them out in the wild, right? So do you have any initial insights into the kinds of workloads that we kind of deployed in our Janus paper in terms of anomaly detection and computer vision? And do you have a favorite workload or something you want to explore more in the future?
Yeah, so as I mentioned before, we had 2 primary workloads. One was the anomaly detection workload, which was a very lightweight algorithm that pretty much looked at the means and looked at variances of the points across that mean. And what that allowed us to do is use sensor data from farms. So we used a temperature sensor and a humidity sensor to be able to find out anomalous points in the data set. And that's pretty important in an agricultural setting, because these points could lead to further actions being taken by other aspects of the farm, which could like make or break the farmer's actual plans for the farm. And on the other hand, for the heavy workload, we had object detection. And object detection is a very popular class in the broad scheme of computer vision, where a region is proposed for a given object, and that the object in that region is classified into one of many classes. And this is also a common task for IoT devices because of especially self-driving cars, which need to be able to detect humans or even objects that are on the road, as well as for like surveillance setups, which is also very important to see like anomalous object detections, right? To have a still frame most times, but sometimes, let's say there's a robbery going on, or things like that. So for security cameras, I think this is also a very important space. For me, I'd say my more favorite workload would be the object detection part of things, because of my recent work in serverless, where we're using such a heavy workload of object detection, but still kind of decomposing it and splitting it apart to be able to run on lightweight, independent functions that as a whole is able to provide an object detection service.
Yeah. So do you think serverless is the way to go? And I'm for one very excited to work at the kind of the interface of computer vision, these kinds of object detection, very practically important workloads on the one hand, and making them work on something that was not initially designed for these beefy workloads, right? And one of the points of serverless is that you pay by compute, right? You don't just time. So you pay just as much of compute as you are actually using.
Yeah.
So I think to end, what is your, attractive attraction related to serverless? And maybe do you think some of the workloads that were not originally designed and created for serverless can be easily fitted for the serverless environment? Because serverless is kind of possibly going to become ubiquitous if we do it the right way.
Yeah, for sure. I definitely believe that there is a big future for serverless because of the simple fact that it abstracts away so many of the pain points from the developer. Like simple things like setting up scalability, right? On Amazon's interfaces, setting up an auto scaling group and then setting up all the rules and the alarms is a very painstaking process. And there's a lot of engineers that, put in a lot of effort to be able to figure out when an application needs to scale, like what needs to happen. And similarly for fault tolerance, running an own custom VM involves so many issues of having to reboot failed VMs or being able to identify anomalous CPU utilizations, things like stragglers in VMs. So there are a class of problems that exist in the traditional cloud space, which serverless pretty much just throws out of the window and says, us as the cloud provider, we're more experienced at this, and we will provide this for you, and you pay for just what you use, and we'll take care of all the heavy lifting. So I think that's a very attractive option for people to develop applications very quickly. And definitely all these complicated applications, starting with object detection, and I think even more complicated like applications like hard data analytics on big data is, I think, a very attractive option because of the parallelism that we can extract out of serverless functions. So Spark jobs, for example, can still be adapted to serverless because of their similar architectures, and there just has to be some work to merge the two together.
Yeah, so we talked a lot about data engineering, but I think data engineering without data science may feel a little bit pale in this quick video of ours. So maybe I'll end saying that, there is a little bit of a flavor of adaptive object detection that is there in the Janus paper. And something that we have done hence is creating this fully adaptive model of a computer vision algorithm that can either aggressively approximate on the fly, depending on the runtime conditions, or not approximate as much, right? And this it does depending on both the content of the video and the contention of the video. And contention is not something that people think of generally, because when they think of these embedded devices or SoCs, they'll be like, hey, maybe I'm just going to use them as object detectors and that's it. But if you thought of cell phones a while back, you might have thought, hey, cell phones are just for calling, right? But I can't remember how much I use my cell phone for calling these days versus some of the other things.
Yeah, absolutely.
Yeah, and maybe that's what's going to happen with these SoCs, where you have these voice assistants monitoring various things on these SoCs. And guess what? When these voice assistants work on these SoCs, they are hogging your GPU. And the GPU is what will be doing a lot of these computer vision applications. So I think two highlights of this chat with Karthik today is one, our Janus paper, where we very intelligently benchmark a bunch of technologies that are very relevant to IoT workloads on the one hand. And on the other hand, we talk about some ways of aggressively approximating some very beefy neural networks that are typically designed for computer vision But thinking of server class machines, or thinking of very computationally well-resourced machines, but not thinking of the possibilities that you might have compute constraints, not only because of the machine itself, the SoC itself, but because you have co-located applications running on the SoC at the same time, or you might have background tasks that are running on the SoC while you want to do object detection on it. So doing both content-aware and contention-aware approximation is something that makes, again, right-sizing the infrastructure as per the desired task. So with that, I think we're going to end today's quick chat with my student, who's now a graduate student at CMU. And it's very nice to see students carry these projects forward and think of ways in which this can impact real world scenarios. In this case, it's IoT, digital agriculture. Think of these connected farms with lots of these IoT sensors, so sensorized farms that are sending their data to these gateways, and these gateways are sending their data to these mega gateways that are aggregating all of that together, and based on that you take the right decisions and you right size everything, right? So I think Janus means having this effective gateway. Janus is from the Roman god gateway, so you are kind of making sure the gateway has the ability to let the right amount of computational resources pass through it, and doing everything in the exact manner that would satisfy both the application and the computational resources on which the application is running. So that's it for today. Thank you.